So I'm going to go through the examples for section 3.4. Part A asks, or number 1, part A says to write the volume of a cube as a function of the side length S. And they didn't give us a picture, but I'll try and sketch one out here. So if the side length is S and we have a cube, then hopefully you all know that V equals S cubed. Part B asks us to find the instantaneous rate of change, which means we're talking derivative, of the volume V with respect to a side S. So the notation we're going to use, instead of V prime, I'm going to use dV ds. And we're just going to use the power rule. So our variable that we're dealing with is an S. So we have 3s squared. Part C asks us to evaluate the rate of change of V at S equals 1. So when we do that, the notation that we use, we draw a line here and we're going to have S equals 1. So this is the notation. And we're going to substitute in a 1 and we get 3. And then we're asked when S equals 5. So dV ds when S equals 5. So we get 75. So part D asks us, if S is measured in inches and V is measured in cubic inches, what units would be appropriate for dV ds? Well, in the numerator, the dV is going to be cubic inches. And in the denominator, we can think of it like a fraction. We're going to have our change in S is going to be measured in inches. So we would say cubic inches per inch. And I know there might be a temptation, oh, I'm going to cancel one of the inches and say inches squared, but that wouldn't make sense for, this is a unit and it's inches cubed per inch is how we would describe the rate of change for the volume with respect to the side. The next problem, number 9, deals with particle motion. So the accompanying figure shows the velocity, and it's important that you think about the fact that we're looking at the velocity of a particle moving on a coordinate line. So part A asks us, when does the particle move forward? So we have to think about what's true. If the particle is moving forward, then that's telling me that the velocity is positive. So I'm looking for where the velocity is positive, and we're looking at a velocity graph. So the velocity is positive anytime that my graph is above the x-axis. So that's going to occur from 0, and we could actually include the 0. So from 0 to 1, and then from 5 to 7, if I write that in interval notation. So we would have anytime that it is above the x-axis. So when is it moving backward? So if it's moving backward, the velocity is negative. So we're looking for below the x-axis. So we've got from 1 to 5 is where it would be moving backward. Where is it speeding up? Now to get where it's speeding up, we're going to kind of go into part B and talk about when the particle's acceleration is positive, negative, or 0. So in order to be speeding up, two things have to be true. The velocity has to be greater than 0 and the acceleration greater than 0, or the velocity and acceleration are both less than 0. So the signs have to be the same for these. And slowing down, we're looking for opposing signs. So the velocity might be positive and the acceleration negative, or the velocity could be negative and the acceleration positive. So then if we're looking at, it's easy to tell when the velocity is positive and negative, we already did that. But we need to talk about the acceleration. So remember the relationship between the velocity and acceleration. So if we take the derivative of velocity, we get acceleration. So what that means is if we look at the slope of the line segments, that tells us the acceleration. So then here, if you notice between 0 and 1, The velocity is positive, but notice I have a negative slope, which means the acceleration is negative. Between 1 and 2, the velocity is negative because I'm below the t-axis, and the acceleration is also negative because I have a negative slope. From 2 to 3, the velocity is negative. The acceleration is 0 because I have a 0 slope. From 3 to 5, the velocity is still negative. Acceleration is positive because notice I have a positive slope on this line piece here. From 5 to 6, the velocity is positive and the acceleration is positive. From 6 to 7, the velocity is positive, acceleration is negative. And from 7 to 9, the velocity is 0 and the acceleration is 0. So what does that mean? So if I want to know where the particle is speeding up, so it's speeding up. Remember when they're the same sign. So from, oops, let's see, not here. So from 1 to 2, union. From 5 to 6, I think that was it. So it's speeding up, slowing down when they're opposing signs. So from 0 to 1, and from 3 to 5, and from 6 to 7. Okay, so we've got speeding up, slowing down. So that was all for part A. Now part B, we've already kind of answered. When is the particle's acceleration positive? So the acceleration is positive from 3 to 6. I think that's it, right? 3 to 6, because it's when we have a positive slope on our line. When is the particle's acceleration negative? So from 0 to 2, and from 6 to 7. Let me get this out of the way. Okay, and when is it 0? We had that from 2 to 3 and from 7 to 9. Okay? When does the particle move at its greatest speed? Now, remember that speed is the absolute value of velocity. So that would mean, like, we could take, now we don't actually even know, we don't have a vertical axis. So we kind of would need to know how high up this is, and is this farther down than this is up? I think it is. So it looks to me like the greatest speed is occurring between 2 and 3. Remember, speed is the absolute value of velocity, so you have to look above the axes and below. So I think that it looks like it's between 2 and 3, that the speed is the particle's moving at its greatest speed. And then part D asks, when does the particle stand still for more than an instant? So we're looking at when the velocity, now be careful, because down here, that's the velocity, it's not standing still because we still have a velocity going on here. But right when the velocity is 0, that's when the particle is still. But now this is just an instant because we're moving forward, and then we're changing directions and moving backwards. The velocity is positive, then the velocity is negative, which actually makes sense why the particle is slowing down and then speeding up, because it's getting ready to change directions. So, but that's just an instant. It's still for an instant here as it's going from moving back to moving forward. But here from 7 to 9, that appears for more than an instant. So we're going to say from 7 to 9. Okay? Number 13, lunar projectile motion. A rock thrown vertically upward from the surface of the moon at a velocity of 24 meters per second. So they're telling me V of t is 24 meters per second. Reaches a height of, and so they're telling me S of t is 24t minus 0.8 t squared. This is the initial velocity, so this is, okay. So that's our initial velocity. So the question part A, find the rock's velocity and acceleration as functions of time. So keep in mind that velocity, remember, is the derivative. So if we want to find the velocity, we take the derivative of position. So we get 24 minus, power rule here, we get 1.6 t. So that's my velocity. To find the acceleration, I can think of that as the second derivative of position or the derivative of velocity. So I get negative 1.6, and this would be meters per second squared. Okay, and I probably should add on here meters per second. Okay, so part B, how long did it take the rock to reach its highest point? Now, you guys used to do questions like this in Algebra 2. If you take a look at the position function, we know that this is a parabola that opens down, and you could find the vertex by doing the opposite of b over 2a. You've done that before, and that you could do that here. You can do the opposite of b, which is negative 24, over 2a, which would be negative 1.6. So you could do that to get the x coordinate of the vertex, or you can think about the fact that if the rock is going up and then it's coming back down, at this moment right here, notice we have a horizontal tangent, which means the velocity is 0. So if you take the velocity and set it equal to 0, 24 minus 1.6 t equals 0, and solve for this, you're going to get negative 24 over negative 1.6. What do you know? So then we get t equals 15 seconds. So on a little side note, suppose we have f of x equals ax squared plus bx plus c. So recognizing our equation for a quadratic. So if you were to take the derivative and with respect to x, so we get 2ax, a, b, and c are constant, so we get 2ax plus b, right? C is a constant. So now let's imagine this was position. Imagine this was velocity, okay? So we want to set this, if we're trying to find the maximum height of our function, then we can take the derivative and set it equal to 0 and solve for x, and guess what? You get the opposite of b over 2a. And that's actually where the formula comes from for finding the vertex of a parabola. And you learn that formula in algebra without realizing, hey, I'm actually using calculus when I do that. So back to our problem on part C, how high did the rock go? Well, if we know it occurred at 15 seconds, then we just want to evaluate S of 15. So when you plug that in, you get 180 meters. And part D, when did the rock reach half its maximum height? Well, its maximum height is 180, so half of it would be 90. So we want to know when this, whoops, equals 90. I'm going to leave that for you. I mean, because you guys can just take this. Nothing real thrilling here. And you've just got a quadratic to solve. When you do that, I'll just tell you, looks like that this is, you can verify this, but you're going to get about 4.393 seconds. I'm going to skip that. It's not really calculus related, but I mean, hey. So how long was the rock aloft? Okay, well, so for part E, we're looking for when the position, when it hits the ground. So then we want to know when S of t equals 0. So we can take 24t minus 0.8t squared, set that equal to 0, and we can factor out a t. So we get t equals 0. We're more interested in this one over here. So we get t equals, and that's going to be 30 seconds. Okay, so that takes care of that problem. I actually have another video for number 19, so instead of doing the problem over again here, I'm just going to attach both videos.